Hey everyone, Morgan here. So we're starting a couple of pages here of discussion about the second law of thermodynamics. Previously we had talked about the first law. The first law said that the energy of the universe is constant. You can't create energy, you can't destroy energy, it's just energy is conserved. Now we're going to be introducing some concepts so that we can discuss the second law. And it begins with a nice little guiding question that we use, okay, for all of thermodynamics. And that question is, if left to itself, will a given reaction happen without outside influence? And the way we can translate that is what we're talking about is spontaneity. Is a reaction spontaneous? According to the dictionary, spontaneity is the quality or act of being spontaneous, which is utterly useless. Doesn't help me. A spontaneous process is one that will proceed on its own without further input from the rest of the universe. One that is thermodynamically stable, okay? And we must note that spontaneity has nothing to do with time. A spontaneous reaction may be very slow or it may be very fast, okay? Diamonds do spontaneously turn back into graphite, okay? But it happens over millions and millions of years, so it's not something we're terribly concerned about. This is not the kinetics chapter. We already took that test. Now all we want to know is whether or not the reaction actually happens. So what are the things that help us determine spontaneity? Well, one of them is temperature. So let's look at temperature's effect on a process. I'm going to have 3 identical beakers. And in each of these 3 beakers, I am going to put an identical volume of water with an identical ice cube in each of them, but I'm going to vary the temperature. In this first beaker, I have 1 degree Celsius water. And I know that if I sit and watch that for a little while, what's going to happen is that ice cube is going to melt. It's just going to happen, guaranteed. Over here at this one, it's at -1 degrees Celsius. And if I sit and watch it for long enough, what I know is that ice cube is going to get bigger. All of that liquid water is going to eventually freeze. And then I'm going to have this one at 0 degrees Celsius. And if I let that one just sit there, it doesn't change. That's an equilibrium situation. Okay? So this one melts. This one freezes. And this one essentially is in equilibrium. So I think we can honestly say temperature affects spontaneity. Okay. Now the next thing that we need to talk about that's going to have an effect on spontaneity is the concept of entropy. Okay? Now, entropy is given the symbol delta S. Entropy is, for lack of a better phrase, a quantitative measure of disorder. Now, that's kind of a controversial definition, believe it or not. There are some professors that would prefer we never use the word disorder, and instead that we talk about the number of possible states in which a system can exist. I think it's a little hard for high school students to understand, okay? I'm going to keep talking about disorder, okay? Now, this is a state function, meaning that we can do a products minus reactants thing if we wanted to. Now, to understand the number of different ways something can be put together or how disorderly something can be, we need to understand that the entropy of a solid is always less than the entropy of its corresponding liquid, which is always much, much less than the entropy of its corresponding gas. The atoms in the solid are very orderly, well arranged, packed together closely. All right, that's orderly. That's not a lot of disorder. But when you put them into the liquid form, that phase of matter, okay, what happens is they get a much larger amount of molecular motion happening. They move around, more freedom to move, okay, and they are just inherently more disorderly. They're messier. And then when it's a gas, oh man, the particles are flying around chaotically all over the place, really, really random, no way to predict where they're going to be. So that's tons of entropy, okay? Now, your bedroom, think about this. Some of you probably have a very neat and tidy and organized bedroom, and some of you live in utter chaos, and that's fine either way with me, okay? But if you have a messy bedroom and you spend a whole day on the weekend cleaning it up, the entropy change equals a negative number. The entropy goes down because you have made it more orderly. Or if you have a really bad week, you don't clean anything, and your room goes from being clean to being really messy and disorganized, you have an entropy change that will be positive, okay? So that is more of interest to us than the just absolute entropy. It's how does the entropy of a process change. Okay, thanks for tuning in. This is Morgan, signing off.